Cable companies typically offer a discounted yearly rate for the first-time internet customers, in hopes that once service is started, the customer will eventually upgrade to the next level. In 2010, new customers to the local cable company in the northern branch were given a discounted yearly rate, while in the southern branch, new customers were given the standard yearly rate. 2 years later, it was discovered that of the 50 new customers from the northern branch, 23 upgraded their service, while from the southern branch, of the 45 new customers, 11 upgraded their service. First thing we want to do is think like a statistician. And probably the first thing a statistician thinks of, or at least one of the first things that a statistician is going to think of, is how was the data collected? Well, let's go ahead and look at the problem. In 2010, notice everything in green. It was customers who signed up to this cable company. There are 2 branches, north and south. Now, it doesn't say that it was random. However, we would consider this possibility right here that they are a representative sample of people who actually want cable service. So in this case, while we don't have the randomness, we can imply that they randomly signed up because it's out of our control. People sign up when they want to, and so we assume that it's a representative sample from the population. Was this an experiment or an observational study? Well, the data is clearly obtained from observation. Cable customers were not selected randomly and placed into control groups. The results of those who upgraded their service with those who did not are observational in nature. They just let time take its course. 2 years passed and then they noticed something. They didn't try to control anything. Alright, first let's look at the conditions for inference. And we need to consider the following. Create a 95% confidence interval for the difference in proportions of upgrade for the 2 groups of customers. Well, one thing we want to do here is consider the population of interest. Population here is people who want a cable service. Alright, now let's consider the following. The conditions for inference have to be met. First one, randomization condition. It's reasonable to assume that since the event of customers signing up for this service are from events beyond our control, that the customers who have signed up for the cable service are a representative sample of people who are interested in such a service. I'm putting those phrases in red for a very important purpose. You see, those phrases in red keep my response in context. I'm talking about customers, I'm talking about the cable service. And so this is the kind of things that we need to do when we give responses specifically for the AP exam. We need to stay in context. Talk about the people, places, things, ideas in the problem. All right, next thing on the list, we have to check the 10% condition. Well, with so many towns and cities having large population sizes, it's safe to assume that 50 and 45 customers from both branches are less than 10% of the total population. Independent groups assumption. We will assume that the northern branch customers have no influence on the southern branch customers, and that the 2 groups are independent. Finally, the success or failure condition. Alright, with the success or failure condition, we're going to let P hat be the proportion of customers in the north who upgraded their service, and Q hat is the proportion of customers in the northern branch who did not. We get 23 and 27, both are greater than or equal to 10. P hat subscript S is the proportion in the southern branch that upgraded their service. Q hat S is the proportion that didn't. And so we get 11 and 34. 11 just pretty much meets the standard, so those are greater than or equal to 10. Well, good, the conditions are met. Under these conditions, the sampling distribution of the difference between the sample proportions is approximately normal. This now justifies using the normal model. So I'll find a 2-proportion Z interval. And now it's time for a word from Boromir of Gondor, the part of the lesson where Boromir of Gondor gives us a word. One does not simply do a 2-proportion Z interval without first checking the conditions for inference. This has been a word from Boromir of Gondor. Thank you. Okay, that was a little bit silly. Moving on. The two sample sizes are 50 and 45. The observed sample proportions are 0.46 and 0.24 repeating. Now we're going to compute our estimates. We want to know the standard deviation for the difference in proportions, but we don't know the true standard deviation. So we use the standard error as an estimator. Using the following formula and plugging in the values that we have, we get that the standard error for the difference of proportions is about 0.0952. Now let's calculate the margin of error. Z critical for a 95% confidence interval is 1.96. So our margin of error is 0.1867. The observed difference in proportions between the two is 0.46 minus the 0.24 repeating, which is approximately 0.2156, and that's how much of a difference we have in these proportions. So the 95% confidence interval will end up being the observed difference plus or minus the margin of error. In this case, that gives us from 2.9% to 40.2%. Okay, time for the summary. I'm 95% confident that the true proportion for those who renew their cable service when given a discount at the beginning of their contract is from 2.9% to 40.2% higher than for customers who upgrade their cable service but were not given a discount at the beginning of their contract. Remember, this interval is about the difference between the proportions. So when you look at the difference of proportions, we notice we get positive numbers, which means the northern branch seems to have a higher level than the southern branch of people who upgrade. When it comes to responses on the AP exam, we basically have three categories of people, more or less. The first one is the nerd. The second one is the surfer dude. And the third one is the statistician. Okay, what on earth are you talking about? Let me try and explain. You see, the nerd understands the math. He uses only formulas to back up his results. And he does not talk about people or units or the context of the problem. The math alone is the reason for the answer. A lot of students respond that way, and unfortunately, these are the students who end up with 2s. The surfer dude may or may not really understand the math. He tries to sound important by making long paragraphs and using lots of words. And he's way too relaxed in defining his results. The statistician, which is what we're striving to be here, what does he do? Well, he understands the math. He backs up his results with evidence. He talks in context about people, places, and things. He doesn't jump right into a problem without the conditions being met. Let's go back here. We need to not be satisfied. You see, we did a 95% confidence interval. Okay, big deal. Why did we choose 95%? What if we had performed a 98% confidence interval of inference? Well, as far as the calculations go, only one thing would change, and that's Z critical. For 98% confidence, Z critical is 2.33. Now, how would that change our interval? Well, our confidence interval would become negative 0.6% to 43.7%. Do you see the problem yet? Well, this means that we are 98% confident that the true proportion of customers who upgrade their service when given a discount at the beginning of their contract is anywhere from 0.6% lower to 43% higher than customers who do not get a discount at the beginning of their service. Immediately, the math nerd's going to key in on this, and he's going to look at the interval, and he's going to see that negative 0.6%. And he's going to say, uh-oh, zero's in the interval. This means there's no evidence that the discount works because 0 is a possible answer for the difference of proportions. So the nerd has a major problem with that. The surfer dude has no clue that the difference needs to be talked about here. He's just going to say, okay, here's my results for this 98% confidence interval. He has no idea that there's an interpretation to be made here. It's the statistician who's going to look at this interval and then compare it to the previous one. Statistician's going to look at this and say, while it is true that 0 is in this interval, the negative value is also very close to 0, and the upper end is very large, so there still may be some evidence to suggest that this discount works in motivating people to upgrade their service later on. Let's talk about hypothesis testing. All right, let's perform a hypothesis test with alpha level of 0.05. Let's give our conclusion and the consequences of committing either a type 1 or type 2 error. First, we do the null hypothesis. So we hypothesize that there is no true difference between the proportions. Otherwise, we assume alternatively that there is a difference between the proportions and that it's greater than 0. Now, why did we choose greater than 0 as the alternative instead of just not equal to 0? Well, the reason was because when we write out our observed proportions, we noticed that we observed that 0.46 really was greater than 0.24 repeating. And so that's why it's justified in saying the alternative difference is greater than 0. All right, well, this becomes a one-tailed test. So we calculate a z-score based upon the difference of proportions, the difference of the observed proportions, minus the null proportion, which is 0 in this case, divided by the standard error. Well, we do the calculation. We get the following z-score of 2.264. And we calculate the probability of getting that z-score, which is 0.012. We make a conclusion now. If this had been due to natural sampling variation, then we would only see this difference about 12 times out of 1,000. That's much less than our chosen alpha level. There is evidence enough to reject the null hypothesis. There does seem to be enough justification to say that if you give a customer a discount at the beginning of their contract, then they might be more likely to upgrade their service later on. And this is how a hypothesis test blended with a confidence interval can reinforce and make your evidence and your conclusions even stronger, supporting the two come together and actually support each other. All right, type 1 and type 2 errors, who's going to suffer from this? Well, a type 1 error occurs when we reject a null hypothesis that is true. So if there really is no advantage for the company to give discounts, but we say otherwise, then the company's losing out on money because they're giving away a discount that has no effect, while the customers end up getting a nice discount. So this is a lose-win situation. Type 2 error occurs when we fail to reject a null hypothesis that is really false. So if there's an advantage for the company to give the discount, but we say that there isn't, then the company loses out on the potential profit from the service upgrades, and the customers lose out on the discount in the first year of their contract. So this is a lose-lose situation.